On the 15th of April 2013, a bombing incident took place during the Boston Marathon, injuring 280 people. 14 of them suffered severe limb injuries that forced them to undergo amputation, making them live the rest of their lives heavily disadvantaged, without the very limbs that most of us take for granted. It is estimated that around 1 in 700 people are amputees without certain limbs, putting the global number of amputees at 11 million. In today's society, the loss of limbs entails severe physical disability, bringing major inconveniences. Amputees often have difficulty completing trivial tasks such as taking a shower or getting breakfast made, while those who resort to using bionic limbs suffer the lack of dexterity. Therefore, they often have to rely on crutches, which can be very inconvenient as it hinders the execution of other tasks. Limb loss also renders people unable to enjoy an equal standard of living, as many of them suffer from various degrees of discrimination. For example, employers are often hesitant to offer jobs to amputees, and would rather offer the job to someone who doesn't suffer from any physical disabilities. Hence, limb loss often bears a psychological impact on amputees, causing problems such as depression, making life a tragedy to those inhibited by their physical conditions. However, any of the physically disabled possess great minds and hearts, and are potentially great contributors to society. Modern prosthetics are far from being affordable or sufficiently functional for their use. It is indisputable that this is hardly fair for people in these unfortunate circumstances. Hence, we see the issue of limb loss to be an urgent issue for modern medicine to tackle. To address this problem, we have decided to dedicate our project to regenerative medicine and artificial organ research, in particular the research of stem cells as a means to regenerate what is lost in these people, not only to help them enjoy an adequate standard of living, but to go above and beyond and achieve their fullest potential. Regarding the topic of regenerative treatment, stem cells are the leading candidate for any potential treatment. But firstly, what are stem cells? Stem cells are undifferentiated biological cells that can differentiate into specialized cells and can divide through mitosis to produce more stem cells. They are found in multicellular organisms. In mammals, there are two broad types of stem cells: embryonic stem cells, which are isolated from the inner cell mass of blastocysts, and adult stem cells, which are found in various tissues. In adult organisms, stem cells and progenitor cells act as a repair system for the body, replenishing adult tissue. In a developing embryo, stem cells can differentiate into all the specialized cells, but also maintain the normal turnover of regenerative organs, such as blood, skin, or intestinal tissues. Compared with other cell types, stem cells have special properties that enable them to be used for regenerating organs. By extracting just a few stem cells from the body, we can cultivate them and let them multiply into indefinitely more stem cells of the same type, until we have enough cells for differentiation and transplant. Now, there are lots of research on stem cell therapy. In 2004, scientists at King's College London discovered a way to cultivate a complete tooth in mice. Researchers are confident that the tooth regeneration technology can be used to grow live teeth in human patients. Success in regrowing cochlear hair cells with the use of embryonic stem cells has also been reported. It is possible to produce larger and more complex organs, such as the limb, through multipotent stem cell technology.
Before we go further, we should clarify on some of our terminology. We use cell potency to describe the range of specialized cells that stem cells can differentiate into. Cell potency is a continuous spectrum, meaning that there are no clear-cut boundaries between each category, but there are generally categorized as follows: totipotency, pluripotency, multipotency, oligopotency, and unipotency. At the top of the spectrum, we have totipotency, which is the most potent type of cell. As far as scientific knowledge goes, the only type of totipotent cells in humans are zygotes, which form when an egg and sperm are fertilized together. However, these cells have the ability to divide and differentiate into all of the cells and eventually make up our bodies. At the opposite end of the spectrum, we have unipotency, which means that the cell can only differentiate into one type body cell. Obviously, if we were to use stem cells for regenerative treatment, then these cells must possess high cell potency, as it allows them to differentiate into all the different cells that are found in a specific body part. Therefore, only totipotent, pluripotent, and multipotent cells should be considered. However, totipotent zygotes are extremely rare, as they only exist for a few days after fertilization, so there is currently no technology that is advanced enough to utilize totipotent cells. There are three other types of stem cells potentially usable for regenerative treatment: embryonic stem cells, tissue-specific stem cells, and induced pluripotent stem cells. However, all of them have their respective disadvantages, which makes them unfit for limb regeneration. Embryonic stem cells are obtained from embryos that were fertilized in vitro, more commonly known as the test tube babies. They are pluripotent and undifferentiated stem cells, as they are not obtained from the transplant subject itself. The transplant of embryonic stem cells may trigger rejection from the host. In order to avoid this, the patient's immune system has to be weakened so that the growth of the implanted cells will not be hampered. However, this makes the patient vulnerable to pathogens, which may lead to the contamination of new diseases. Additionally, due to the high potency of embryonic stem cells, their growth is often rapid and difficult to control. This can result in the formation of cancerous oncogenes, which may form tumors. On top of that, there is also controversy surrounding the ethical issues of using embryonic stem cells. Therefore, embryonic stem cells are not suitable for regenerative treatment. On the other hand, tissue-specific stem cells, also known as adult stem cells, are found among differentiated cells in the tissue or organs from adults. They are less likely to cause implant rejection if these stem cells are patient-matched. However, adult stem cells are scarce in adult bodies, so it requires careful cell cultivation in order for there to be sufficient stem cells for potential regenerative treatment. These cells also have to be nourished, so they require additional proteins for nutrition. However, these proteins are often extracted from animals. If these animal proteins are used to treat adult stem cells, humans may contract animal diseases after implantation. Moreover, adult stem cells also need to be treated by viruses. This may lead to the formation of tumors, which can be extremely detrimental for the patient. Lastly, we have induced pluripotent stem cells, which are artificially reprogrammed from adult cells. They essentially have the same pluripotent properties of embryonic stem cells, which makes them good candidates for regenerative treatment. They have the advantage of being patient-matched, which reduces the probability of causing transplant rejection. This also means that we don't need to weaken the patient's immune system in order to avoid rejection. However, one major flaw is that induced pluripotent stem cells require the use of viruses for cell nutrition and to reprogram adult cells into induced pluripotent stem cells. This is clinically unacceptable, as this may result in the formation of tumors. As each of the previous 3 stem cells are either hazardous or impractical for regenerative treatment, through our research, we have come across the new form of stem cell technology known as induced multipotent stem cells. These cells are in many ways superior to the 3 other types of stem cells.
Induced multipotent stem cells, abbreviated as iMS cells, are stem cells that were recently pioneered by researchers at the University of New South Wales. The process of producing iMS cells requires extracted fat cells and involves the use of the chemical 5-azacitidine and platelet-derived growth factor AB. What AZA does is that it increases cell potency and relaxes the hardwiring of the differentiated cells by switching off their memory, while PDGF-AB reprograms the differentiated cell into an undifferentiated iMS cell. Compared to embryonic stem cells and induced pluripotent stem cells, iMS cells have lower cell potency, thus making their growth easily controllable. This prevents potential tumor formation in the patient. Also, iMS cells do not require the use of viruses for nutrition, lowering the chances of tumor development. Another point is that fat cells are abundant within our bodies, so we can extract a large amount to be converted into iMS cells. These iMS cells can also be patient-matched if we extract the fat cells from the very body of the patient itself. As a result, implanted iMS cells have a low risk of rejection, making it safer for the patient.
The full process of the regenerative treatment involves extraction, conversion, and implantation. Firstly, fat cells, shown in yellow, are extracted from the patient through liposuction. We then take these fat cells and treat them with AZA, shown in red, and PDGF-AB, shown in green, for a period of 48 hours. After that, we remove the AZA and continue treating the fat cells with PDGF-AB for another 2 weeks. This process converts the fat cells into iMS cells, shown in blue, until all the extracted fat cells have become iMS cells. Next, we take these iMS cells and implant them into the patient's shoulder, the site closest to the patient's missing arm. Over time, these iMS cells will proliferate, producing more copies of themselves. At the same time, some of these cells will start to differentiate into the yellow arm cells. On a larger scale, the number of differentiated arm cells will gradually increase until there is a sufficient number of differentiated cells to fully regrow the arm. Let us consider the hypothetical case that we encounter an amputee who requires a new arm to be grown. In order to estimate the time that it will take for an arm to grow after the implantation of iMS cells, we first have to determine the number of iMS cells that have been converted from fat cells. There are on average 50 billion fat cells in the entire human body. We know that the average density of our bodies is around 1 gram per cubic centimeter. If we divide this amount from 62 kg, which is the average mass of a human body, we find that the average volume of a human body is around 62,000 cubic centimeters. Next, we have found out that typically a single liposuction procedure can extract around 150 cubic centimeters of fat cells. Therefore, we can take the total number of fat cells in the human body and multiply it by the volume ratio between the extracted fat and the entire human body. This would give us a rough estimation of the number of fat cells that were extracted through liposuction. If we assume that 100% of these fat cells can be successfully converted into iMS cells, then the number of iMS cells that can be implanted is 121 million. We can also estimate the total number of cells in an arm. We picked out all the cells that existed in arms listed as follows. By summing up all these different cells, we got a total of 36.3 trillion cells. However, this includes the number of cells across the entire human body, not just in the arm. In order to solve this problem, we assume that the mass of one arm is approximately 2.5% of the mass of the entire human body. Therefore, we can multiply 36.3 trillion by 2.5% to get a rough estimate of the number of cells in an arm. Now, let us examine the process that iMS cells go through once they are implanted for arm regeneration. We start off the process with 121 million iMS cells. We can assume that these iMS cells don't die because their lifespan usually lasts several years, and our process of growing an arm doesn't require that long of a timescale. With this assumption in mind, we know that during a specific cell cycle, iMS cells can either differentiate into specialized cells, such as muscle cells or blood cells, or they can proliferate, in other words, undergo cell division to become two daughter cells. These proliferated cells are undifferentiated, so in the next cell cycle, they can again differentiate or undergo further proliferation. This process essentially continues forever unless there are no more undifferentiated stem cells left to self-renew. During the first cell cycle, a certain percentage of these iMS cells will proliferate into more stem cells so that their amount is doubled. Let's say this percentage is represented by P. Therefore, the number of undifferentiated or proliferated stem cells after one cell cycle is given by 121 million times P1 times 2. The remaining percentage of these cells would differentiate into body cells. Let's say the percentage of cells that differentiate is represented by D. Therefore, the number of differentiated body cells after one cell cycle is given by 121 million times D1. During the second cell cycle, these undifferentiated stem cells can once again either differentiate or proliferate. In order to get the number of proliferated cells, we multiply 121 million by P1 times 2, then by P2 times 2. In order to get the total number of differentiated cells, we take the sum of all the cells differentiated in the first and second cell cycle. As we calculated before, the number of cells differentiated in the first cell cycle is given by 121 million times D1. The number of cells differentiated in the second cell cycle is found by taking the number of cells proliferated from the previous cell cycle, which is 121 million times P1 times 2. Then multiplying by D2. Notice that P and D are both functions instead of constants. This is because the percentage of cells that proliferate and differentiate change over time. We will elaborate on this in more detail later. Following the trend we just observed, we can obtain the following formulas. Here is the formula for the number of undifferentiated or proliferated cells during a particular cell cycle. We have 121 million as the starting number of stem cells, multiplied by the total product of all the proliferation percentages, multiplied by 2 to the power of t, which is the number of times that the stem cells have divided through cell division. Here we have the formula for the number of cells differentiated in a particular cell cycle. Once again, we have 121 million as the starting number of stem cells. However, this time we multiply by the total product of all proliferation percentages before the current cell cycle. Similarly, we multiply by 2 to the power of t minus 1, which is the number of times that the stem cells have divided prior to the current cell cycle. Then lastly, during the current cell cycle, a percentage d of all these stem cells will differentiate. This is the formula for the total number of differentiated cells over all previous cell cycles. Here, the total number of differentiated cells is simply the sum of all the cells that were differentiated during the previous cell cycles. Therefore, we just take the summation of the previous formula. Since we have now come up with the formulas, we have to define the values of P and D, which are functions of time. We know that cells are adaptive according to the environment as well as the need of the host. In our case, the patient requires a full arm to be grown quickly, so the iMS cells will proliferate more rapidly at first, generating more cells that can be differentiated later. When there is sufficient number of iMS cells proliferated, more cells will differentiate in order to form tissues in the arm. Therefore, the proliferation percentage P will decrease. Eventually, the proliferation percentage and the differentiation percentage will both become constant. At this point, the system reaches steady state, with the number of cells going into the system, which is the number of cells differentiated every day, being equal to the number of cells going out of the system, which is the number of differentiated cells dying every day. This is to ensure that the size of a fully grown arm doesn't keep increasing. Based off the premise that the proliferation percentage decreases over time, we can conclude that P is the function that decreases over time from 1, if we assume that 100% of iMS cells will proliferate when time equals 0. We have found two possible mathematical functions that fit this description, a negative linear function or a negative exponential function. Between these two types of functions, we chose to use the negative exponential function, as we know that the rate of change of proliferation is not constant. This cannot be modeled by a linear function, which only shows a constant rate of proliferation. On the other hand, a negative exponential function decreases sharply at first, levels out later on when it reaches its horizontal asymptote, essentially becoming constant. This makes the negative exponential function suitable for modeling the proliferation percentage P. Since iMS cells can only differentiate or proliferate in any given moment of time, the sum of pt and dt must equal to 1. Therefore, if we know the function of p, we can also find the function of d by subtracting p from 1. We can now substitute the functions of P and D back into our three formulas. We now notice that there are two unknowns, M and T. Therefore, we must require two equations in order for these unknowns to be solved. Recall that we previously estimated the total number of cells in an arm to be 907 billion. If we equate this to the formula for the total number of differentiated cells, we can obtain our first equation. In our model, we also specified that the system will reach steady state, N equals out, when the number of cells differentiated every day is equal to the number of differentiated arm cells dying every day. Now, in order to estimate the number of arm cells dying every day, we first use the lifespan and percentage abundance of each type of cell, and sum them up in order to calculate the average lifespan of all cells found in an arm. We found that the average lifespan of all arm cells is 5 years, approximately equal to 1,826 days. If we divide this number from the total number of cells in a fully grown arm, we can estimate the number of differentiated arm cells that die every day. When the system is in steady state, the number of cells dying every day will equal to the number of new cells differentiated every day. Therefore, we can equate this number to the formula for the number of cells differentiated every day in order to obtain our second equation. We now have two equations which we can use to find the two unknowns M and T. However, they cannot be easily computed as simultaneous equations, as the two equations that we have are rather complicated non-linear equations. Therefore, we attempted to solve for the two unknowns by using the method of trial and error, which got us the following values. 62 is the time required to fully regrow an arm in terms of the number of cell cycles. However, since one human cell cycle takes 24 hours, we know that approximately 62 days are required in order for an arm to be fully regrown from iMS cells. As there is still a huge number of patients with missing limbs desperately waiting for treatment, the development of regenerative technology is of paramount importance. iMS cells are superior to other alternatives as they're not cancer-inducing or ethically controversial, so we hope that it can be popularized in future so that a good number of patients with missing limbs can benefit from it. Though our mathematical model is far from perfect, it is still effective in illustrating the general process of using stem cells to regenerate lost body parts. Perhaps in a few years' time, we may see limb regeneration become a norm for previously injured people to resume their normal lives.